So what you are supposed to do for each scatter plot is decide which of the two lines graphed are a better fit. Normally, we have to put that line ourselves. We have to put it, and I'm not going to tell you the criteria. Hopefully you remember it from yesterday. But there is certain criteria for what is the best fit line. So table 9 on graph 1, would the solid or dotted be the better fit? Right, class, we agree with that? And table 9, why the solid one?
That's looking for dots where it's closer to the solid than solid.
So the data is closer to the solid line than the dotted. The best fit would be a line that is going through the middle of the data where the points seem to be clustered around it. So if you don't remember that from yesterday, we write it down again where it says best fit. On your constructed response, for example, you will have to draw a line of best fit on a scatter plot, and you will get the points so long as you're going through the middle of your data and your points seem to be clustered around it. All right. So yeah, it should kind of follow, like if you can tell whether it's going up or down from left to right, it should go in that direction as well. Kind of like a slope. All right, these are straight lines. You should be able to estimate the slope and line-intercept. That's what we kind of covered yesterday. We'll continue covering it today. But the line of best fit goes through the middle and the points are clustered around it. Table 1. For graph 2, which one is the better fit, the solid or the dotted? The solid again. I don't think you were the reporter, but solid, because this top one, I mean, they're both pretty close to the data, but the dotted one is above almost every single data point. We want some to be above and below it. The points need to be clustered around it. So yes, the solid one for the second one. Who is the reporter? Okay, I thought it was wait. Anyway, table 2 for graph 3, solid or dotted is the better fit. Dotted. This dotted one is more in the middle. It has points above and below it. So it's not important that it touches every single point. Not even that it touches the most points. It just has to go through the middle and the points need to be clustered around it. So the blue just isn't quite as good. And then table 3, graph 4, which one is best? All right, class, we agree with that one. When you compare it to the solid has only a couple points below it, and then the rest are above it. So that wouldn't necessarily be my middle. All right, questions on this warm-up? Do we know how to tell if it's a good fit or not? This unit is a lot of vocabulary. There are some calculations, but really it's just a lot of conceptual stuff. So know how to make a line of best fit. We are doing lesson 5 today, which is about fitting lines to scatter plots and finding the best linear model. When we were doing it by hand yesterday, I mean, we were trying to make the best one, but there was a lot of variations in our answers because it just depends on how you drew your line. Are we going to draw our lines the exact same way as each other all the time? All right, no. So that's why there were some variations in our answer, and there's always going to be one that is best. The one that is best is made with technology. So we're going to learn how to use technology to find the line of best fit. But really, you can only use technology if you have a table of data. If you don't, then all you can do is that estimating, which we did yesterday. And then of course, describe the rate of change and y-intercept, but this time in terms of the real world situation. I'm recording right now, I record every day, so make sure that you are keeping up with the class, taking notes for every lesson, saving those notes for the binder check. The practice is in Schoology. And you do have a quiz tomorrow over the first 5 lessons, which today is the 5th lesson. Okay, that's our only quiz for this unit because next week it's already. So definitely don't lose your notes. Maybe you save them for about a week more. Make sure they're clean. All right, and I know yesterday we were pretty much doing notes the whole time. We didn't quite get to do the end of the notes yesterday, but I think it's okay because 1, it's recorded from last year, so you can check it yourself if you want. And 2, we're gonna do it by hand first to cover that part we didn't necessarily get to emphasize, and then we can do it with technology after. All right, so the weight of ice cream sold at a small store in pounds X and the average temperature outside in degrees Celsius Y are recorded in the table. For this data, we're going to create a scatter plot and sketch a line that fits the data well. So scatter plots, it's those dots. It depends on what your coordinates are. But notice that these are not labeled. So let's label it. What title needs to go on my x-axis? What are the x's in this situation? The pounds of ice cream sold, yes. So down here, you always want to include your units. And then also pounds of what? So pounds of ice cream sold. And it's our X because they labeled it as X, so we just kind of have to go with what they say. Really, in my opinion, I think that if we're comparing these, I think the temperature is more independent than the pounds of ice cream sold, but that's just not how they labeled it. So we just kind of need to follow how they labeled it. All right. So that is on my x-axis. What title needs to go on my y-axis? What are the y's in this situation? The temperature outside. And we do usually like to include our units. I'm a little bit out of the know, but it's in degrees Celsius. Now, before you start putting dots, we need to decide how our tick marks should be labeled. We need to use an appropriate scale. So that should include your data, and it shouldn't be like too big or too small. So look at our x's. Our smallest x value is 17, and our largest is 21.5. Do I have enough little tick marks here to just count them by ones? Well, if you count, no, I don't. So how do you think I should count by? What would be like the next best? I would think 2s would be better than 5s, just because then 5s might make it a little too crunched together. I do think we have enough to count by 2s for each tick mark. So it'd be like 2, 4, 6, 8. I'm kind of crunched on space, so I'm not going to label every single one, but each tick mark is 2. Okay, like 10, 12, 14, 16, 18, 20, 22, and that covers all my data, but just know like every single check mark is going to be 5. And of course, this is 0. Where it starts is 0. 0, 4, 6. Well, All right, now for my temperature outside, look at what my Y values are. My smallest one is 3.5, good, and my biggest one is. So do we want to count these by ones? Or can you think of something like even better? I do think 0.5s might be better for this situation because again, you don't want your scale to be too big or too small. If you counted by ones, I mean, it probably wouldn't be the end of the world. But since some of our values are 0.5, let's just use as much space as we're able. So each tick mark will be 0.5 here. I'll only label like every other one. So here's 0.5, 1, 1.5, 2, 2.5, 3, and so forth. And we have just enough to get to our last highest data point right at the top. Okay. So usually either in the description or on the graph, it'll tell you what X is and what Y is. We'll definitely use that later when we talk about the everyday language of what these values represent. But for right now, you just need to make a scatter plot. So all of these are coordinates. So this one is 20 minus X. Find where that is and plot it. Dot. I'm going to freeze my screen and then continue doing it. Hopefully you know how to make a scatter plot, how to plot points. If not, someone at your group I'm sure knows. Ask me. Okay, so I finished my scatter plot, so that means yours should be almost done, I hope. If you need help, let me know. And luckily our axes are labeled right now, so hopefully that makes it easier. Otherwise, it's always X to the left, so your horizontal axis is your X axis, and Y to the side. Vertical one is your Y axis. All right, and then your scatter plot should look something like mine. I mean, do we always put our dots in the same exact spots? Maybe like one is off a little bit to the left, but they should definitely be within the proper tick marks. Okay, something like that. So we made the scatter plot and we have to put the line of best fit where we think it's going to go through the middle of our data and our points are clustered around it. Now, you want this to be as straight as possible. I have like a little line tool, so it's a little easier for me. You use another piece of paper, something else that's like straight. If you have a ruler, sure, use that. But you definitely want it to be as straight as possible. And going through the middle of your data where your points are clustered around it. Notice like on your practice test for this unit, you have to add it in and you'll have to estimate it too. So good practice for that. So once you've drawn your line of best fit, and luckily today we have grid lines, so it should be easier to find two parts of the line that we can see very easily without having to estimate. Yesterday we found multiple coordinates, but you really only need two. Okay, it could be a data point, but only if that data point is perfectly centered on the line. And it might look more centered on your paper, the way that you drew it, who knows? But on mine, the only one that might be perfectly centered would be maybe this one for a data point. But otherwise, like I might lean more toward, let's see. This looks perfectly in the middle of the grid line. So where that is would be 26.5. So again, it doesn't have to be a data point. It can be if that data point is perfectly on the line, like right in the center of the grid, but you just need 2 points. So there's one, let's use that one. What's another one that we could use? So is there anywhere else that we wouldn't have to estimate that much? 12-0. All right, works. All we need is 2. And it can be different points. Again, so long as they're from the line, not necessarily having to be a data point unless that data point is perfect on the line. So you picked 2 coordinates, and yesterday I told you a formula to help you estimate your line of best fit. You don't have a whole lot of space on your paper for this. If you have room under the warm-up, maybe this is where you could write it, because we have like where we're estimating it and then finding it with technology. But what's the formula for any straight line? Not for just the slope. Sorry, I didn't mean to confuse you by mentioning the slope formula and now asking you something else. And also, side note, my first hour was really frustrating me, not gonna lie, because I was walking you guys, not you guys, I was walking them to like a certain conclusion, but it's almost like they were not paying attention. And the things I was asking them to recall, while you may have learned it in middle school, we also just talked about it in the last unit. So like there's no reason that some of these answers should be so like lost on everyone. Okay, so just stay with me. Anytime it's a straight line, what formula do we use? Okay, good, because it's linear. We're making linear models. Linear equations are in the format y equals mx plus b. Which of these letters are usually replaced with numbers? Good, M and B. So that's why we are going to estimate the slope. and then we will estimate the y-intercept after. But while you might know slope as rise over run, that could still work if you like that. I taught you this one yesterday, which I think would be better since it's also your average rate of change and it exists the rest of the school year. This will be a formula for the slope that you have to have memorized, and you'll use it like the rest of high school. So you might as well just start memorizing it now. So to find your slope from coordinates, you're going to make one of them x1, y1. The other one, x2, y2. And then you're going to plug it in and solve it using this slope formula. Are you all with me? Taking notes on it? It's too hard to try to teach you things all over again. And you could like pay attention the first time, that'd be really good. Okay. So the way that I labeled it, my y2 is 0. My y1 is 6.5. My x2 is 12. And my x1 is 20. Notice like the ones from the same coordinate are on top of each other when we're about to subtract. You can use a calculator for the math on this. Hopefully I'm not blowing anyone's mind by subtracting 0 minus 6.5 is negative 6.5. What's 12 minus 20? Okay, great. And then use your calculator to get a decimal for the slope this time. This time we don't really want it to be fractions, and you'll see why eventually. All right, but a negative divided by a negative is a positive. So 6.5, negative 6.5 divided by negative 8 is about 0.81 if we were. Sorry, I know I'm like all over the place. This is what my slope estimates to, 0.81. Questions on that process so far? All right. If we have the y-intercepts like showing on our graph, then we could just use that approximate location. Can I see my y-intercept on this graph? Where do we find the y-intercept? On the y-axis. So is my line touching the y-axis? No. So unfortunately, I can't just look at it and say, oh, the y-intercept is about this number. This is where you actually have to do a little bit of math, but that's okay. You can solve for any variable so long as it's the only one. So for that, I would need an x and a y. We just found the slope. So the slope is 0.81. And you can use one of the x and y's that you used earlier. So say I want to use this one. My y being 6.5 would have to go here. That's what y is. The x being 20. And we're doing this to estimate the b, the y-intercept, because I don't have it showing on my graph. So then in your calculator, you're doing 0.81 times 20. Which is about 16.2. So I have 6.5 equals 16.2 plus b. How would I get the b alone? Subtract 16.2 and do that on both sides. When I do that subtraction, my y-intercept ends up being negative 9.7. And in first hour, we used different coordinates. We got that our slope was about 0.78 and that our y-intercept was -9. Notice that our values are close and we don't expect them to be exactly the same. In fact, if they're exactly the same as the person next to you and you take your test, I'm going to be a little suspicious that you just copied them. Because the odds of getting the exact same answers using all the exact same numbers is pretty crazy. All right, but this is my estimated linear model. If this was a question on the test and I was grading you all, I would just want your answers to be close to it. It doesn't have to be exactly it. Questions on that? Okay. Now I'm going to show you a technology, which again only works if you have a table of values. So this whole process we just did, you still have to know how to do because not all the time are you going to have a table of values to put into Desmos. But any questions on the by hand stuff? Good. Okay. YouTube is a great resource. Like if you have your own graphing calculator that you plan to use for state testing, because remember, state testing doesn't let you use Desmos. Just Google whatever model you have and how to make a line of best fit. For Desmos, what you have to do is add a table. So you see this plus sign? We're going to click it and hit table. And know that like I can't necessarily tell you this during the test. Like I can't tell you tomorrow during the quiz. So you would have to either write down the steps. You do have room under number 3 on your paper to write down some steps. Miss Medina. She never made it to my classroom. No problem. But okay. So you're gonna hit the plus sign, add item. It pulls up a table. You are going to transfer this to Desmos. So like my XY pairs, I'm typing it in, making sure that I'm not messing any up because then that would change my line of best fit. All right, so everyone see how I just put the table into Desmos. Like nothing crazy happened. They're still paired with the same numbers. Any good? Everyone good there? Now this next part, by the way, if you zoom out, so I'm gonna full screen for the rest of it, you can see our scatter plot. It doesn't look quite like the one on our paper because they're using different tick marks. If you ever want it to be the same exact tick marks, hit this little wrench. And where it has like values for the x-axis, you could put where it starts and where it ends. So like if I want my x-axis to start at 0 and my highest was about like 26, then it could go like that. And then my y-axis started at 0 and then ended around the 8. And now it looks more like what's on your paper by adjusting the window. All right, but in order to put the line of best fit, this is really important. This is where you might want to write at least this part down if you haven't already under number 3. You're going to click in a different cell and type in Y1 squiggly line, MX1 plus B. So basically it's Y equals MX plus B, except for in order to make it do stuff, you have to put Y1, X1, and the little squiggly instead of an equal sign. All right, so I would take notes of typing that in. And you don't have to do anything special with the one. Like if you literally just type in Y1 into Desmos, it automatically makes it a subscript. And the squiggly. Guys, sit up. I'm not doing this for me. Stop looking at your phone, Aiden. Okay. Anyway, once you do that, you can see the line is drawn through the middle where the points seem to be clustered around it. And when you look at these statistics, what do we notice? What does M stand for? So this is telling me my exact slope, not just an estimate from when I did it by hand. This will tell me the best fit always. So for my one with technology, you can put this formula under number 2. It's y equals 0.78x plus, or not plus because it's negative, minus 9 point, and it just depends what you want to round to. We could do minus 9.44. So compare that to what we got by hand. When we estimated it by hand, we got 0.81x minus 9.7. So would you say that they were pretty close? The closer it is, the better. Like that means the better we estimated it. But the technology will always give you the best one every time. So you might need to put your future in. All right, so write down your technology model. That goes under number 2. Hopefully you jotted down some steps for how to do it in Desmos. Otherwise, you can watch the recording later. Now we're going to use that to answer questions. So 4 and 5. The values for the slope and y-intercept, use what we get from the technology. We did it by hand because yesterday it was like rushed, so we did it again. With the technology, our slope was 0.78. And our y-intercept was negative 9.44. Now tell me in like your own words on your paper what each of these mean in the situation. So like 0.78 what? Negative 9.44 what? Okay, relate it back to the situation about the ice cream and everything. That's your test question, essentially. Then it says use the best fit line, so the one that we did with the technology, to predict the y value when x is 10, and then tell me, is this a good estimate for the data? So make sure these are answered completely. When I explain it and we go over the answer, I'll give you some tips to make that process easier, but this really isn't going to work unless we try to prove it yourself. So 4 and 5, I'll give you about 3 minutes. Talk to your group if you need to, and respond. So I gave you time to engage with it, to ask your group. I will explain it in a way that I think is easier. But for right now, table 4, can you tell me what the slope means in this situation? 0.78 what? Okay, do you guys agree with that? That 0.78 is on the ice cream? Some saying yes, some saying no. So here's a way to help you. There's lots of formulas for slope. Like you tell me some formulas I'm giving you for slope. So that slope intercept form, what about just the M? It is the rate of change formulas though. Okay, good. So the new one I asked you about. Also in the past, we've called it rise over run. And also we've done change in y divided by change in x. Notice on the top is always something about the y. On the bottom is always something about the x. So if your slope isn't in fraction form, make it a fraction. And then it's always how the y variable changed over the x variable changing. So what does it say on our y-axis? The temperature outside in degrees Celsius. Maybe I should just usually abbreviate. So degrees Celsius, I usually use the units because that's usually what it is. And then what was the X? Oh. Pounds of ice cream sold. So what this means, and yes, slope is rate of change, so it's how something is changing in the situation. The temperature changes by about 0.78 degrees Celsius for every 1 pound of ice cream sold. On average. So for every 0.78 change in the temperature, there's about 1 pound sold of ice cream on average. Does that mean that is the same amount that happens every single time? No, it's an average. But your slope has y over x, you should mention both. It's how often the y changes for every increment of x. Questions on that? You know, I don't think we'll have. So whatever it is, if it's, don't necessarily write this down, just pay attention. If it's distance compared to time, all right, y over x. So maybe it's the distance changing for every 1 increment of time. Whatever it is, y over x, always mention both. Questions on that? Hopefully that makes it easier on your test. Always y over x. Now for your y-intercept, where do you normally find your y-intercept? Yes. What about on a graph? Where do I find my y-intercept? The y-axis. It has a coordinate. So if this is my y-intercept, what is it as a coordinate? Our coordinates have 2 numbers. So this is where I started losing my mind first hour because they kept telling me 1 number. If that's my y-intercept, what's the coordinate? Or where it is on the graph? What order are coordinates always in? Okay. For every y-intercept, what is the x value? Thank you. And then if this is my y-intercept, then that's my y value. Right? For every y-intercept, your x is 0. Look at your y-axis. All those x's are 0 there. Then think about what each one represented. X was your pounds of ice cream. Y was your temperature outside. So when it says, oh, what does the y-intercept mean in terms of the situation? You say, this was the temperature outside when 0 pounds of ice cream were sold. Mention both again. It's always whenever x was 0. Okay, good. Any questions? All right. That's like 2 questions on your test. What does the slope mean? What does the y-intercept mean? Rate of change. Whatever this is when x is 0. All right. Now it says use the best fit line to predict the y value when x is 10. So linear models, we use them to predict other stuff. This was the one we got from technology, so we're going to use that one. It's technically more accurate than the one we estimated. What do they want us to plug in? 10. And where do they want us to plug it in? The x. And then now that there's only one variable, which is y, then you should be able to get a value for it. And it's just a prediction. It's not like, oh, that will for sure happen when they sell 10 pounds of ice cream. But we use linear models to predict things that we didn't necessarily gather in our data. Hopefully you know how to use a calculator because the calculations are really not hard this unit. So that estimate, if you got it right, was negative 1.64. How you know if it's a good fit or not is look at how loosely our data was compared to the line of fit. You could also look at it in the calculator too. Would you say that all the data is pretty close to the line? Yes, in both situations, when we did it by hand and when we did it online. Whenever it is close to the line, it's a good estimate. It's a good fit. So you could say yes, because the data is close to the line. The closer it is, the better. In the next few days, we'll also give you other ways to quantify how good it is. But basically, the closer it is to the line, the better our predicted values are. The dots are our actual data. The line is our predicted model. All right, I'm gonna have you do the cool down, but before I give you more directions on the cool down, do we understand? Does this make a little bit of sense? I don't know. Hopefully, I feel like you just need to practice it, but if there's something glaring, we can talk about it. All right, on your cool down, the first question is just asking you which one would be best represented by a linear model. So, oh, side note, maybe I'll tell you later. Let's look at our cool down first. The first one's asking which one would be better represented with a linear model. So this one, that one, or this one, and why. And then for this one, you have a table of values on your paper, but that doesn't actually go with this data. So please cross out the table of values because we can't use it. It's actually not matching this data at all. So do not use the table of values that's on your paper. Cross it out. All you have for this question is the graph and these options to pick from. But these are great test questions. So do them. Pick which one would be best with the linear model and which of these options would be the best fit for that one or for this graph. We'll go over it in about 5 minutes. Should you finish early, work on your practice, but definitely don't put your notes away until we've gone over it. Like I said, these are great test questions. Table 5 of these 3 options, which is the best one for a linear model? And why the third one? Okay, so when you hear the word linear, what do you guys automatically think of? Straight lines. So the one that is the most like a straight line that I could clearly see if it's going up or down from left to right would be this one. And when I draw a linear model on it, most of the points are close to it. So yes, if I tried to do a linear model on the others, it might look something like this. Or like this one's hard to tell even if it's going up or down from left to right. So I'd have to just kind of guess. The last one is the most linear, so it'd be best to model it with a linear function. All right, next one. Questions on this one? If this is a constructed response, make sure you explain your reasoning. The most linear, gotta be close to it. Something along those lines. Now, this one's a great test question because kids always get confused. They're like, I don't see my answer as one of the options. Like they estimate it and they don't see their answer as one of the options. We know that there are variations in our answers, but that they should still be close. So there should be some that are obviously not going to be the answer. If I were to draw a straight line on here to make a linear model, so trying to draw it through the middle of our data where our points seem to be clustered around it, we can eliminate some right away based on the slope. Would the slope be positive or negative? So I shouldn't pick A that has a negative slope. I could automatically eliminate that one. The rest are positive, but like I know for sure it shouldn't be it. Then look at your y-intercept. I can't see it on my graph. What is it approximately? The way I drew it, 10. Now, negative 34, I would say is way too far off. That'd be like somewhere down here. So I'm going to eliminate B for that reason. Between these two, like 10 is kind of in the middle of both. I would probably need to do the actual map for the slope to pick which is best, which is still possible. You can do that. Pick two parts that you can see pretty clearly. So like this one is 450, and this one over here is 550/70. When I label them x1, y1, and the other as x2, y2, and put it in that formula. I'm rushing, so sorry. Y2 minus y1 over x2 minus x1. I get 20 over 150, and that should be closer to one of the decimals. Which is 0.13, if you care. C is the best answer.